Hi everyone. Today we are going to start off with a binary tree series, right? So binary tree, as you must be knowing from my previous video, is nothing but a hierarchical data structure. And this topic is very important when it comes to interviews. Most of the questions that are asked from the topic of trees are usually around easy to medium level. So the way we are going to learn binary trees is that we are going to break down this topic into some 8 patterns, right? Data structures and algorithms is easier to learn when you are able to break down them into patterns, because patterns are finite. That means there are a limited number of patterns which are available. Most of the question which you see in coding usually can be tracked back to one of these patterns. So in trees, I have divided this trees topic into 8 patterns. As you can see, the first one is recursion based. Second is traversals, which also includes the views of the tree. Like for example, you can traverse, how you can traverse an array. In similar fashion, there are different ways in which you can traverse a binary tree. Third is construction of binary trees. Fourth is basically trees. Dynamic programming is a way of approaching your problems. Now using binary, you can use dynamic programming to solve certain trees questions. The famous ones are like path sum. Fifth one is binary search trees. So binary search trees is a special kind of binary trees which we'll learn about, and there are some questions, around 4 to 5 questions, which we'll be doing under this pattern. The sixth one is linked list. Now some of you must be surprised why linked list is a part of binary trees. So there are around few questions where the question usually is to translate the binary tree into a certain way of a linked list. So we're going to look at even those questions. Seventh is serialization and deserialization of a tree. Now this is usually done, to be able to, save your tree and, transport across the network. So we're going to look at how you can serialize a binary tree and deserialize a binary tree. The last and the most important is the trie. So most of you, some of you who know what a trie is actually would be very scared of this topic. But I'm here to help you walk you through this trie topic. For people who do not know what a trie is, it's again a data structure which is based on binary trees. But this trie, you can have a practical application. For example, you when you go to Google and when you search something, you get this autocomplete, right? So the autocomplete search bar. This is actually based on the trie data structure. So we'll solve some questions in tries as well. So around we have 8 patterns, and in every pattern, I'll be at least solving 3 to 5 questions, right? So let's begin our binary tree journey. So now we are going to start off with the first pattern in trees, which is called as recursion based. Recursion based pattern is nothing but you're going to solve the trees question using with the help of recursion. Simple plain recursion is going to be used to solve our binary tree questions. So I have around 5 to 7 questions in this pattern. So let's begin with the easiest one. So the first question which I have chosen is from Leetcode. It's a standard question. The name of the tree of the question is same tree. So let's read the question. Given the roots of two binary trees, P and Q, write a function to check if they are same or not. So they have also defined what they mean by same. Two binary trees are considered as same if they are structurally identical and the nodes have the same value. Right? As you can see in the example here, the first example is said that if you have two trees which have been labeled at P and Q, so the root of the tree is one is P and another one is Q. These are structurally identical and the data is also similar, right? Whatever structurally identical, what does this mean is, suppose one of the tree has a structure of like this, okay, and the second one has the structure like this, right? Suppose like this, and let's say this. Now this also has 3 nodes and this one also has 3 nodes, right? But the structure of these two trees is not same, right? So what we mean here is structurally identical means the way that nodes are arranged in the binary tree, that needs to be same, right? So along with that, so when you say the two trees, let's say this is tree 1 and let's say this is tree 2, we can say the two trees are identical when the structure is same, and also whatever data you can find in the nodes, they have to be similar. That means here if I have a data as 3, so this also needs to have data 3 for it to be same. If this is 4, then this has to be 4. If this is 5, then this also needs to be 5. So then I can say, if I have a similar setup, then I can say that T1 and T2 is going to be a same binary tree. Right? So let's talk about how we can solve this question by using a simple recursion. Right? So let's start with an example. So let's draw this tree, right? And this is a second tree. Let's take an example of which we had just taught about 1, 2, 3, and the other one is 1, 2, and 3. Correct. Let's go back and see what we are given as a in the what all parameters we are given for that function. So there is a function called Symmetric Tree which we have to kind of finish, and we have to return a boolean value. True means that the trees are same and false means the trees are not same. You're also given, you do not have to actually construct a tree node, that is already given to you or done in terms of in the question itself, which is there in the comments. As you can see, the definition for the binary tree node is, so they are calling it a class as tree node. Each of the tree node basically has a value. That value is nothing but is going to store the data, right? Like 1, 2, 3, like integer numbers. Tree node left and tree node right. So what does this mean? Tree node left and tree node right. It just means that this one is going to point into another tree node, okay, and that reference we are basically storing. So as the binary tree, if you recall from the explanation of what a binary tree is, if it's a binary tree, you can have at max 2 children, correct? So it can be a left child and the right child. So that's what they're meaning by this. Key tree node left is the left child, tree node right is the right child, right? And then you also have some constructors here. You have a default constructor. You also have parameterized constructors, which you can use to initialize your tree node class, right? So I'm just explaining this for the first time so that if somebody who's not aware of what a tree node is and how to define a trees, then this is how it is, right? So, and if you also recall, we had two ways of representing trees. One was using an array, and the another one was using classes and objects. So obviously here they have used the concept of classes and objects, right? So now we have two trees, P and Q, and we're given the we're given the reference to the root, and now our job is to find out whether it is same or not same. So let's say this is our P, okay, and this one is nothing but our Q, correct? Now our job is to find out whether it is same or not. So according to the definition which we just discussed, the data needs to be same. So what you're going to write here is, let's say you have a function, right? So you have P and Q as a functions, right? So I mean, you have a function, the name of the function is like you can say any name, and you have this two trees, right? P and Q, correct? So first thing you're going to do is you're going to compare the data, right? So if P dot data, okay, the first thing needs to be, this needs to be equal to Q dot data, right? Because if that is not equal, then there is no need to check the structure at all, right? So this is where we're checking the data. So if this is equal, what needs to be checked? Because we want everything to be true, right? We want the data in the nodes to be same, and at the same time the structure also needs to be same. So when you have more than one condition which you need to be true, you use the logical AND operator, correct? Now next what you're going to do is, from here you can access the left child, right? How do you do that? We say P dot left, and here you can say P dot right. Similarly for Q, you can do Q dot left and Q dot right. So you're going to say the data needs to be same, and at the same time you're going to call the function, because now you have to check whether this part, the left subtree, right, this left subtree of the P tree, okay, needs to be equal to the left subtree of the tree which has been rooted at Q, right? So both the subtrees also needs to be equal, both the left and side. So here I'm going to call same function, I'm going to call for P dot left, right, and Q dot left, right? If you remember from recursion, if you know what recursion is nothing but when you want to do the same task again, just that the data at what you are trying to feed for the recursion, it's going to kind of reduce in size. For example, initially in this recursion, the first call is going to have the entire tree P and the another tree Q. What we have done is, now we have checked the data for both the roots, right? We have said that okay, the root data is same, which we have checked here. Now what is remaining is we have to just check whether the left subtree, okay, is equal to the left subtree of the Q tree, right? If both are equal, then we have checked one more condition. The last condition we also have to check is whether the right subtree and the right subtree of these two are equal, right? So what you do when you have to just do the same thing, right? So that's why I'm calling recursion here. So I'm going to again say AND, because I want this condition to be true as well. So I'm going to say P dot right here and going to pass in Q dot right. Right? So what I'm doing here is basically, checking my data, and this is going to do the job of checking data plus structure. Correct? Let's try to, take an example and debug so that becomes a little clear. So when you are having this tree, right, which we just saw, which is 1, 2, and 3, and let's say this is your P, correct? You had your 1, 2, and 3, okay, and this was your Q. Right? The first condition, it will be like whether P dot data is equal to Q dot data. In our case, this is going to be true. So what is going to happen is this particular part is going to return the value as true. Next, what is going to happen? There will be a function call. You're going to go to the p dot left and q dot left. That means, let me use a different this. So now you're going to have a different function call. This is where your p is pointing in that function call and q is pointing here. Correct. Now this is a function call to the same function. So that means again you're going to check this whether p dot data is equal to q dot data. Is p and q's data same? Both are true. So you're going to say what? Again, this value comes true. And now you're going to go to the left hand side of p and similarly to the left hand side of q. Now if you see that these are leaf nodes, so there are no what to say, it's null, right? The left child of both p and q are null, right? So that means if there is null, we have to kind of handle that situation, correct? Because if you do not handle, what is going to happen is, let's say you do not handle this and this is going to call p dot left and q dot left. What is going to happen is you will be having a null pointer exception. Here what will happen is you will try to say null dot data. Now you cannot, this does not make sense, null dot data, right? You will have a null pointer exception, and this is what the mistake usually what people do. Right? You can also think about it in this way. When you're writing a recursion function, one of the important part of a recursive function is that you need to have base conditions. What is base conditions in recursions? You can think about those as constraint or the stopping conditions which you give for loop, right? Usually in a for loop, you mention whether, like I is going to 0, I is less than n, I plus, right? So this I less than n is nothing but is kind of a condition which is going to finally make sure that the for loop terminates. Similarly, in recursion, base conditions are nothing but you can think about those as those conditions that where finally your function calls are going to stop and you're finally going to return some value, right? So that your recursion does not go infinite. So here, if you can look at the example, what we need base conditions is if p is equal to null, right? And even q is also equal to null. What we need to do? If it is null, both of them are null, so can I simply return true? What does this mean? It means that if both my trees are null means there is no tree at all, right? So if both of them are null, then I can definitely say that's true. By default, if there's nothing, then I can say that those two trees are same, right? That's what I mean by that. Now assume if, let's say, both of them are not null, it's possible that p is null, all right? And let's say q is not null, okay? Or else we can have a situation where p is not null, right? And possible that q is null. Can we have that? Yes. If this is a situation, what do you think we should return? We should return a false, right? Because p and q are not basically same. It means that there's nothing there in the p node, but q is not null. Q might have some, referring to some data. If this is the case and p is referring to null, then obviously these are not same, right? Because nor the data nor the structure is matching. Similarly, if p is not null and q is null, then also they cannot be considered as this. So, right? So how do I put this in code? I can simply say if p is equal to null, right? Or q is equal to null, right? So if one of them is equal to null, if or means what is going to be true when one of them is equal to null, right? So I'm going to say return false. Right? The reason I'm saying return false here, okay, is because I will make sure that both of them are not null at the same time. Why? I'll make sure that this condition when both of them are null is checked before. Because if both of them are null, I want to make sure to return true because then they are same trees. But then the second condition here, I've written this key, okay, here when I come to this condition, it means that both p and q are not null. Only one of them will be null, right? I hope you get this, and that's why I've written here if p equal to null, q equal to null. Think about this. If you have the first situation where p is equal to null and q is equal to null, right? According to your code, you're going to first check the condition whether both p and q are null, right? When this condition is this, you're going to simply return true, and which should be the case. So our condition is met, right? You're going to return from here. You're never going to check the second condition. Let's say now p is null and let's say q is not null. Right? What is going to happen? This first condition, whether p and q are null, is not going to be true. This is not going to be true. It's going to be, you're not going to, this value is not going to evaluate to true. So you're not going to go inside the if condition. So the next condition you have is whether if p is equal to null or q is equal to null, right? So in this case, our p value is equal to null. So this is going to give a true. This is going to give a false. True or false is true. So when this is the case, you're going to simply return from here the value as false, which you definitely want, because if one is null and another one is not null, then the trees cannot be treated as, same trees. So this is basically these two conditions will be your base conditions, right? If actually whatever nodes you're trying to compare, if they do not fall, in these two categories, so obviously the category which needs to be considered is this one, where you have to check the data of both the nodes and make sure once the data is compared, you go and check the left subtree of the tree, that needs to also be same, and then you go and check the right subtree as well, right? And understand, because of the beauty of this logical operators in Java, what happens is, suppose in case this particular value, right, if this in case this value is false, okay, it can be possible, right, that this value, they have given you the value as false. If this is false, obviously Java is not also going to make a call to these, right? I hope you know how this logical operators work. If one is false, wherever it finds a false, it's going to simply return false, because for a logical AND operator to be true, all the inputs, all the conditions to the AND operator need to be true. So that means wherever any of the condition is false, it's going to stop there, and you are going to save on making, you're not going to make any function calls further, right? Or let's say, assume that the data was equal, but let's say might be the left subtrees of both the tree which you're like to look at are not equal. Then this suppose returns a false. If this returns a false, so there is no need for us to go and check the right subtree, right? Even if it is equal and not equal does not make sense, because for a tree to be equal, right, we want that both the data and the left and the right subtree, everything has to match, right? So I hope you get this, right? So let's try to write code for this particular question. It's very simple now, right? Whatever we just discussed, I can write. So what is the first thing? Let's write the base conditions. So the base conditions would be if p is equal to null and q is equal to null. The reason I'm using and, because I want both of them to be null. If that is the case, I can simply say that yes, they are equal, and I can return true. Suppose that is not the case. Let's say only one of them is null, right? So if I want only one of them to be null, I'm using an or, and I'm going to return simply false from here, right? Because then they cannot be a same trees, right? Let's say my whatever trees I'm trying to look, and they do not satisfy this base condition. So obviously they are not null, and I have to check the actual condition, which is basically I'm going to say simply return whether p dot value has to be equal to q dot value. That means I'm checking the data. At the same time, if this is equal, I'm going to call the function again. So I'm going to say is same tree. I'm going to check now with the left subtree, right? So p dot left, and I'm sending q dot left, right? So this is my, and then I'm going to also check is same tree and make sure, suppose let's say if this returns as true, that means that my left subtree of both the trees are same. I have to also go ahead and check whether the right subtree also matches, right? And let's say this is q dot right. So this is all which I will need to code, and if I just submit this, it should absolutely work. It's actually accepted, and that's what, and it's also suggesting the next question. Okay, so let's discuss a little bit about the time complexity. Right, if you look at this, what is this question doing? This question is actually you're traversing each and every node of the tree. Correct. In other words, if I have to talk about time complexity, it's going to be that whatever nodes are there in the tree, I'm going to visit each and every node. So my time complexity is going to be equal to the number of nodes I have in the tree. So that is my same tree. Obviously, for space complexity, you are going to have space needed for the recursion stack, right? And how long your recursion stack can be. I hope if you remember from how recursion works. In recursion, what we do is that suppose if you have a recursion like this, right? This is your binary tree, okay? And you're trying, and these are the two trees right here, right? Usually how recursion does is it is going to make sure to complete one end before it starts returning back, right? So this actually looks like what is your recursion stack is going to have at a time the height of the tree. Whatever is the height of the tree, that many recursive calls you can have at max in the stack, and that much is the space you would require for your recursion stack. So that will be basically your space complexity for this question, right? I hope you understood this. Just give this question a try. About the next question, which is symmetric tree. So given the root of a binary tree, check whether if it is a mirror of itself, right? That is symmetric around its center. So they have told us what a symmetric tree means. So if you can see a tree like this in the first example, like you have this 1 2 2 3 4, right? So you have to, they have put a mirror here. Can you see that dotted line? That is nothing but a mirror. So you just have to answer the question whether the left half, that means your left subtree, is it a mirror image of the right subtree, right? So just pay attention to how that tree is looking. If you look at this, you had a tree like this, right? In the thing there's a 1, right? So there is 2, there was 2 here, there was a mirror which is kept here, right? Let's have that with a red line. So this is our mirror, correct? I hope everybody understands how a mirror image looks like, right? Whatever is on the left appears to be on the right, whatever is on the right appears to be on the left in the mirror, right? So when you say whether it's a mirror image or a symmetric image also, we are talking about in terms of mirroring, correct? That's what the question is trying to tell us. So with the question example we had here is, so 1 2 2. So let's draw first the left subtree for this tree, and then we can draw the right subtree. So in the right subtree, okay, this is what is given to us in the question, and they have said that this is actually a symmetric tree. Okay, it's a symmetric tree. If you have to make an observations here, if you can see, whatever is on the left, right, actually becomes on the right, right? Whatever is on the left becomes actually on the right because we have a mirror here, right? So this is actually the right, this is actually your right child, which has actually become your left child in the that part of the tree, right? So this particular question, right, if I have to solve this is very similar to the earlier question, which was same tree. If you have not seen that part, just make sure that you look at that question and come back here. In that thing, we had 2 trees and we had to check whether the 2 trees are equal, right? And we had done it using simple recursion. Here also you can do the same thing. Here what you can say is that your P can point to the left and your Q can point to the right of this root node, right? Why? Because within the same tree only we have to check whether this tree is basically symmetric across the center, and the center is this side. Center is actually passing through the root node. So what we'll have to check is, if you have to see whether the 2 trees are which are these 2 subtrees P and Q are basically symmetric, or whether they are a mirror of each other, all we have to do is the data needs to be same. Can you see here? So the P dot data will be equal to Q dot data, right? For the same tree, what we had done is, like, we called the function again and we passed in P dot left and we also passed in Q dot left. But here we have to make a slight change. Why? If you can see, whatever is present on your left hand side actually needs to be present on the right hand side of the Q, correct? So what needs to be sent here? P dot left needs to be compared with Q dot right. That's the only change. Here, if you have checked with left and right of this P, you have to now check with P dot right needs to be checked with Q dot left, right? For example, from the diagram, P dot right needs to be be equal or compared with your Q dot left, because we are basically looking at the mirror images, or in simple terms, symmetric images, right? So let's come back to the code, right? It's very easy. So let me just remove this. I actually have the code here for whatever we had written for symmetric tree. Just copy pasting that because I just have to make a change, right? All the base conditions and everything remains the same, correct? So when P dot value and Q dot value needs to be same, obviously, because if there is one node, can you see here the node number 2 in the first example, that node number 2, both is same, right? So that is what I'm referring to. Your value needs to be same, and then your mirroring actually is happening with your left and right subtrees, right? So P dot left needs to be checked with Q dot right, and P dot right needs to be checked with Q dot left. And here it's symmetric, so I'm just changing the name here, symmetric, and it's symmetric, right? So if I submit this, it needs to be submitted. Oh, did we miss something? Yes. So what we have done here is I'm calling for this. So here what I've done is there's only one function, right? So let's call this function control X. Let's have one more function here. You can have this function as, let's say, Boolean, and we can give it as solve, right? And let's say we have tree node P, okay, and we have tree node Q, okay, and here we can just paste this. If this is solve, control C, control V, control V. Here what I need to do is I have to return what, solve whatever my root dot left, right, and root dot right has been there, correct? You just make sure that if the value is possible, that the value of this root only is null, right? So if your root, it's basically null, right? If your root is null, so obviously you simply return I think it's true, right? Because otherwise if root is null and if you try to do root dot left, it's going to give you a null pointer exception, right? So let's now try to submit it. Yes, it works fine, correct? So you just saw that I did copy paste and I kind of missed that this particular function has only one parameter, right? But if I have to check symmetric, I'm just, comparing with the left subtree of the root and the right subtree of the roots. And that's why I created one more function here, gave it two values here, and that's what I've done. Right, just make sure to come, before I send this, I just check the null value, because it's possible that the root can be null. So if I do null dot left or null dot right, it's going to give a complaint saying null pointer exception. Right, hope this helps. Even the time complexity analysis for this will be very similar to your same tree, because you're going to actually visit each and every node of the tree. So if there are n nodes in your binary tree, the time complexity is going to come up as O of n. Again, when it comes to space complexity, because this is recursion, you will need some space to store your recursion stack, and your recursion stack will be nothing but equal to the number of function calls at a time in the recursion stack will be equivalent to what is the height of the tree. And as you know, the height of a tree can be anywhere between log n to O of n. If you remember from the first discussion of what a binary tree is, we discussed some concepts which was height of the tree, and height of the tree for a skewed, binary tree can be O of n. So your recursion stack will also, for your space complexity, can also be anywhere between, in the worst case scenario, O of n, if in case your binary tree is skewed to either right or is skewed to either left. Hope this helps.